Hello learners, welcome to the course of MIO 002. So in the first session we talked about how the data science is going to help you for smart cities world. Today's session we will be talking about how the big data, particularly big data analytics, is going to helpful for smart cities. In that I'm going to talk about the case studies where we will be talking about how the big data is going to helpful for the transportation system, where I'm going to talk about what is a probe data, what is enriched data particularly, and in this case study I'm going to talk about how the data was collected, what are the different areas we have covered, and what are the different regions for those site selection, and finally we will be able to see the visualization using public Tableau. So if you look at the 68% of the world population which are projected to live in the urban areas by 2050, which is set by the United Nations, it means there will be a tremendous growth in the digital ecosystem of the organization. So discipline of data science, particularly big data and machine learning and other technologies are actually going to helpful for the process of collection, integration of these data, processing of large amount of data to produce some kind of useful decision making information, so that particularly these useful information can be helpful for the making decision. So smart city is a technologically modern urban areas that uses different types of electronic methods and sensor to collect the specific types of data. So if you talk about the big data, so big data is more real time in nature than our traditional technologies. So when I say traditional technologies, we are particularly talking about the data warehouse technologies. In that, data warehouse technologies are not really well suited for storing the huge amount of data, particularly when your database or data size is huge in volume. For example, you have exadata, teradata, which are not very well suited for the big data application. So in that case, the big data is actually going to helpful for that. So shared nothing environment, massively parallel processing, scale out architecture are the well suited environment for the big data application. And especially when we talk about the big data has a three important characteristics. One is volume, second one is velocity, and third one is varieties. When we say volume is basically the size, because today's this data is actually growing day by day. So you need a particular technology which can actually helpful for storing these kind of data. And when we talk about the velocity in terms of the speed, because the amount of data we are receiving very faster. So do we have a technology which can actually store or which can actually receive these data in the same manner or not? And the third characteristics, that is the varieties. That means we are talking about, not only we are talking about the structured data, we are actually talking about semi-structured data, we are talking about unstructured data, where the big data is mainly concerned for. So big data, not only it is going to helpful for storing the structural data, it is also going to helpful for storing the unstructured data such as audio, video, image, text data as well. So what is big data in transportation? Today, transportation data uses many technologies to store the data or to monitor the different traffic conditions. They uses different sensors, they uses cameras. So let's talk about how this big data in transportation is actually going to helpful for this. So big data in transportations, where the data is large and complex, and we need this big data technology because the traditional database technologies are not really suited for storing these complex types of data. So mainly we have a 4-dimensioned, as I mentioned in the last slide, I said we have a 3 important characteristics: volume, velocity and variety. But when we actually talk about the big data, not only those 3 important characteristics, we also have another important characteristics known as veracity. So veracity, which refers to the pre-processing of data, which refers to removing the noise from the data. So unless your data has a quality data, you are not going to get the quality output. That's the main thing. So for example, if you talk about volumes, today if you really see that at Chicago, which generate approximately 35 million traffic records every single day. So it's a huge data. So you need a technology which can actually store these amount of data. And when we say the velocities, for example, if you talk about the analysis of data, there are approximately 500 million tweets every single day. So there has to be a technology which can not only process these tweets in this case, and also able to analyze those tweets or those data. So we should be able to store different forms of data. So not only the structural data, we should be able to store the semi-structural data, unstructured type of data, where we should be talking about videos, social media data or sensor data and all. Then comes to the veracity, which says that no quality data, there is no quality results. Because today's in the real time, 30% of the data collected is not at all useful for real-time decision-making system. So what we have to do? So you need a different types of techniques which can helpful for removing these kind of noises. So what was the actual motivation? So if you really look at the motivation part, how the big data can help in transportation. It can help to manage better traffic. It can help to detect the incident. It can improve the traffic safety. And not only that, it can also helpful for real-time feedback. So this is how the big data technology in transportation is going to helpful. So these are the different motivation which has motivated us to work on these data. But whenever we talk about these big data in transportation, there are challenges. The challenges which includes capturing, storing, searching, sharing and analyzing these big data and all. And big data actually address the 2 basic problems. One basic problem is the storage part. So how we are going to store the big data. And the second important part is the processing part. How exactly you are going to process that. So there are various technologies which can helpful for not only for the storing, it can also helpful for processing these big data and all. One such technology is known as Hadoop, which uses a cheap hardware, right, which actually uses your old system and integrate all those systems using those Hadoop clusters, and then it can be used to store the big amount of data. So if we ask you what is a probe data is basically a crowdsourcing method where we use the different devices and different vehicles to collect the data, which covers the different interstate, state highways. It stores the speed and travel time data and uses the traffic message channels to store these different real-time data. So what the INRIX provides? So INRIX is particularly a vendor, right? It's one of the vendor which actually uses different technologies to provide the speed, travel time, incident, quality data updates along with each mile long travel segment, at a frequency of once in every 20 seconds. That means for every 20 seconds, your mile-long travel segment is getting updated with speed of that vehicle, travel time, if any incident happened, all those things will be covered by this INRIX. The resulting stream is approximately 9 to 10 GB per month, or more than 100 GB per year for the entire Nebraska roadway system. So if you consider one of the transport department at Nebraska roadway system, they are actually storing 9 to 10 GBs, and these are the text data basically. So how this data look like? So data of INRIX, which is like an input file, has a different fields. It has a TMC code, which signifies the specific location. Then you have a date and time, you have a speed, you have a average speed, you have a reference speed for that particular route, then you have a travel time, then you have a confidence score, then you have a C value. And if you look at the confidence score, other than what you have as TMC code, date, time, speed, average speed, and reference speed, so confidence scores give you the three different types of data. So if the confidence score is 30, it actually gives you the real-time data, which signifies the real-time data. If it is 20, it's a combination of historic and real-time data. If it is 10, it means it's a historical data. So many times what happened where you don't have a real-time data, it actually gives you the historical data of that particular route. So for this particular case study, we have taken the real-time data, which means score 30, confidence score 30, for the major criteria to select the site or location here. So what was the main case study here? So we are moving from traditional sensor-based technology, which are mostly static, to the GPS probe data, which are dynamic in nature. We know that sensors which are fixed at particular location will be capturing the speed of a vehicle, whatever the speed vehicles pass by that particular sensor will be recorded. But in case of GPS probe data, which are dynamic in nature, has a direct contact with the server, and with the help of that, it actually store, not only that, it takes the date and time, it store the speed, it store the average speed, reference speed, along with the travel time and confidence scores and all. So that was the main region. And if you really look at if one can say that one can fix the traditional sensor in the different locations, but you know that installing traditional sensor in a different location is a very costly affair, right? So in that case, definitely we would like to move from traditional sensor based technologies to the GPS, which are the probe based data, right? So let's look at the probe based data versus traditional sensor data. So if you look at the graph, so we just want to check the two things here. One thing is whatever the data we are collecting from the probe data are actually reliable or not, whether it is actually collecting the real-time data or not. So if you look at the orange color, which are showing you as a traditional sensor data, then you have a probe data which are in a blue color, which is showing you the different types of data here. And in this case, what we have, so presently your transport department is maintaining around 65 automatic traffic recorder, which covers the different locations, right? So this covers the entire state of Nebraska, where you have a 65 automatic traffic recorder, right? And where he collects the speed, date, time, incident, average speed, and so on, confidence score and so on. Like all those things will be stored by these automatic traffic recorder, which are definitely a reliable way of storing. So our main question is, whatever the data we are collecting through the probe data through the GPS device or GPS probe device is actually reliable or not. So for that, what we did here, so if you look at the diagram, one of the performance measures we have collected is the congested hour, and where you have more than 500 GB of data, and these data we have collected from the traffic data. And what we did, we have used the Hadoop technologies for the data streaming and pre-processing things, and where we have used the Hadoop distributed file system, that is HDFS, and we have used the Apache Pig technologies for the pre-processing the data and all. And for congestion detection algorithm, we are which are again divided into the two parts, which are recurring congestion and non-recurring congestion. So recurring congestion, where the speed is less than 45 miles per hour, and based on the dynamic threshold, which are less than speed. Not only that, we have also verified with the camera images for the verification, right? And for the non-recurring, again the speed limit we took was speed is less than 45 miles per hour, and again this has to be checked with the dynamic threshold, and this we have verified with the Department of Transportation incident report verification system. So recurring, which are expected during the peak hours, and non-recurring is basically which are unexpected. This might be due to work zone lane closure, this might be due to the adverse weather conditions, etc. So if you look at the data coverage, collection and site selection part, so what we did was Transport Department, which are presently maintaining 65 automatic traffic recorder in a different locations. And we know that the cost of deploying and maintaining these sensors are very, very high as compared to the probe data. And probe data collection is a set of relatively low cost methods for obtaining the travel time and speed data. So with the help of INRIX, which maintains around 4125 traffic message controls or centers, which help us to collect the traffic information for the major freeways and urban areas. So if you look at the Webtronic sensors during the data collection, this was the vehicle we have used, and where you can see that in the middle part there is a sensor, and in the top we have also used the cameras which was using to record all the vehicle information and all. So if you look at the graph here now, this shows the percentage wise availability of INRIX in a transportation department for the year 2016. Now you can see that this is the Nebraska states, which covers, and you can see that different colors combination here. So you have a yellow lines, you have a red lines, and you also have a green line, right? So green line signifies the real-time data in this. So particularly we have taken this particular route of the green route, and you can see that this was coming from this is covering actually I-80 route, Interstate 80, and you can see that you have divided into two parts, the whole Nebraska state, which we have as an interstate and non-interstate here. And you can see that percentage wise distribution of real-time data. In case of interstate, we have almost like 78% of data, but for the real non-interstate, we have hardly 3 to 4% of the data as real-time data. So what we did, we consider the interstate highways for checking the reliability of probe data, and different locations are identified based on the different conditions, different criteria. So criteria 1 was the ATR midpoint, ATR which is automatic traffic recorder. So from ATR midpoint we have actually taken the location to the traffic message centers, that is TMCs, and from that midpoint we have collected whether the data is actually coming or not. Criteria 2, which is automatic traffic recorder data. Criteria 3, we have also considered the winter segments. Criteria 4, we have also seen the level of confidence available in the particular areas based on the different scores, score 10, 20 and 30, and we said that confidence level 30 is basically a real-time data. Not only that, we have also taken the another criteria which has helped us to select these locations. So what we did, we have tried to find the anomalies from the different graphs. We have taken the CDF distribution graph for better decision making. We also consider the number of heavy truck and interquartile range for each of these TMCs. And if you look at the graph here again, this map shows the 16 specific locations in the transportation department, which is covering 16 sensors and 32 TMCs, one for the left side and one for the right side. And once we have processed these data, what exactly we did, we have used the public Tableau. So Tableau is a powerful and fastest growing data visualization tool, which has actually helped us to build this dashboard for that. So if you look at this dashboard, which is covering the 16 different locations out of 65 locations. On one side, top left side, you can see the automated traffic recorder here, and these are the traffic recorder. If you select one of the traffic recorder, you can see the reliability curve for that, which we have taken based on the CDF distribution curve. And then we have also considered the traffic message channel here, TMCs. For that particular traffic recorder, we will be able to see what is the average annual daily traffic data, what is the confidence level 30 proportional data, and what is the distance from the ATR mid location and all. So based on the different 5 criteria, we have selected these locations and all. One of the such interesting things we analyzed was the congestion hours for the westbound and the eastbound. Interstate 80 in 2013, 2014, 2015 and 2016. So you can see that there are peak hours where you have in 2013, 14, 15 and 16. This was a time where there was a winter time, and red color shows the what you call the summer time, and blue color shows the winter time here. So winter time, you can always see that there is more traffic and all. We have also given the order here. So based on the probe data, that is a PBR sensor data and index data, we have compared the different sensors and the TMC segment here, and we have calculated the congested hour for those particular things, and we found that almost there is no change in the congested hour for those particular days and time. This is another analysis we have done, where you can see that interstate 80 interstate 80s, we can see that there are different sensors located, and for each sensor there are 2 TMCs, one for the left side or east side or west side, and another one we might be having the different locations. So this entire interstate will be covered by these TMCs and all. So particularly if you look at what exactly we discussed here. So we discuss about how the traffic monitoring are going to be useful for wide area probe data source, which is actually growing here. And real-time data, probe data is actually useful for traffic operations and safety management activities. such as travel time estimation, incident management system, and whatever the information we gain from these big data technologies are used to manage the asset, are used to manage the resources and services efficiently. In return, the data is going to helpful for improving the operational cost and take the better decision system. So big data in particular helpful for all the traffic conditions, safety, managing what you call travel time estimation, and managing the incident management system in particular. Thank you.